We live in a universe that's full of stars. I mean, really full of them. In our galaxy alone, there are something like 100 billion stars, maybe more. And beyond our galaxy, there are hundreds of billions of galaxies, each one packed with billions of stars. That's an enormous number of stars. Now, here's the thing that makes it interesting. If you pick any direction in the sky and you look far enough, shouldn't your line of sight eventually hit a star? Think about it like this. Imagine you're standing in a forest, and this forest goes on forever in all directions. If you look in any direction, eventually you're going to see a tree trunk, right? There's no gap. Every single direction your eye can point, there's a tree somewhere along that line blocking your view. You can't see through the forest. Now, if the universe goes on forever, and it's full of stars distributed more or less evenly throughout space, then the same thing should happen. Every single direction you look, your line of sight should eventually terminate at the surface of a star. The whole sky should be covered with stars. Not just little points of light here and there, no. Every single point in the sky should be glowing as bright as the surface of a star. The entire night sky should be as bright as looking directly at the sun. But it's not. When you look up at night, you see mostly darkness with little bright points scattered around. That's the paradox. This thing has a name, by the way. It's called Olbers Paradox, named after a German astronomer, Heinrich Olbers, who wrote about it in 1823. Though, to be honest, he wasn't the first person to think about it. People had been puzzling over this for a couple hundred years before Olbers. There was this English fellow, Thomas Digges, back in the 1500s, who thought about it. And Kepler, the same Kepler who figured out how planets move, he worried about this problem too back in 1610. Now you might say, wait a minute, Feynman, I've got an answer for you. The stars that are very far away, they're just too dim to see. The light gets weaker as you go farther out. And that's true. The light from a star does get dimmer with distance. It falls off as 1 over the distance squared. If you go twice as far away, the star looks 4 times dimmer. That's absolutely correct. But here's the trick. Here's the beautiful part. Let me show you why that doesn't solve the problem. Imagine we divide up the universe into a series of shells, like layers of an onion, all centered on Earth. Each shell is, say, 1 light year thick. Now the stars in the second shell are twice as far away as the stars in the first shell, so each star in the second shell looks 4 times dimmer. But here's the thing. Because the second shell has a bigger surface area, it can fit 4 times as many stars. So even though each individual star is dimmer, there are more of them, and the total amount of light from that second shell is exactly the same as from the first shell. You keep going out shell after shell after shell. Each shell contributes the same amount of light. If the universe goes on forever, you've got infinitely many shells, so you should get infinitely much light, or at the very least enough light to make every point in the sky bright. So the distance argument doesn't work. The dimming with distance is exactly compensated by having more stars farther out. All right, maybe you're thinking of another solution. What if there's dust out there between us and the distant stars? The dust could absorb the light and block it from reaching us. That was actually one of the ideas people suggested, but that doesn't work either. And the reason is pretty straightforward. If you've got dust sitting out there absorbing all this starlight, it's going to heat up. It has to heat up because energy is being pumped into it. And when something heats up, what does it do? It radiates. Over time, that dust would get hot enough that it would start glowing just as bright as the stars themselves. So you're back to the same problem. What about this? Maybe the universe isn't actually infinite. Maybe it just stops somewhere. Kepler thought about this. He said, well, if space is finite, if it has an edge, then when you look in certain directions, your line of sight just goes out into empty void, and that's why you see darkness. But this doesn't really solve it either, not completely, because we can see that the universe is enormous. Even if it's not truly infinite, it's big enough that we should still see a sky much brighter than what we observe. We've got hundreds of billions of galaxies out there. That's plenty enough to fill up the sky with light. So what's the answer? What's really going on? Well, the real answer is beautiful, and it tells us something fundamental about the nature of the universe itself. There are actually 2 parts to the solution, and they're both connected to one amazing fact. The universe had a beginning. First, let's talk about the age of the universe. You see, the universe isn't infinitely old. It's about 13.8 billion years old. We know this from a whole bunch of different measurements, and they all agree pretty well. Now, light travels at a finite speed. It goes fast, sure, about 300,000 kilometers per second, but it's not infinite. It takes time for light to get from one place to another. So here's the key. We can only see light from stars and galaxies that are close enough that their light has had time to reach us since the beginning of the universe. If a star is 15 billion light years away, well, its light hasn't gotten here yet. The universe simply hasn't been around long enough for that light to make the trip. So there's a limit to how far we can see. We live inside what you might call a light bubble. We can only see the stuff within that bubble, the stuff that's close enough that light from it could have reached us in the 13.8 billion years since the Big Bang. That solves part of the problem right there. There aren't infinitely many shells of stars contributing light. There's a limited number of shells, the ones within our light bubble. But that's still a lot of stars. That's still hundreds of billions of galaxies. Shouldn't they make the sky pretty bright anyway? Here's where the second part comes in, and this is really marvelous. The universe is expanding. This was discovered by Edwin Hubble in the 1920s. He found that distant galaxies are all moving away from us, and the farther away they are, the faster they're receding. The universe itself is stretching, getting bigger. Now, when a source of light is moving away from you, something interesting happens to the light. It gets redshifted. The wavelengths get stretched out, made longer. You've probably heard of the Doppler effect with sound. When an ambulance drives toward you, its siren sounds higher pitched, and when it drives away, the pitch drops. The same thing happens with light. When something is moving away from you, the light gets shifted toward the red end of the spectrum, toward longer wavelengths. In an expanding universe, the farther away something is, the faster it's moving away from us, and the more its light gets redshifted. For the most distant galaxies, the ones that are billions of light years away, the light gets redshifted so much that it's no longer visible light at all. It gets shifted into the infrared, into the microwave part of the spectrum. Our eyes can't see it anymore. So even though there are galaxies out there, even though they're shining, their light has been stretched by the expansion of the universe to the point where we can't see it with our eyes. That's why the sky is dark. The light is there, but it's been red-shifted out of the visible range. In fact, there's this wonderful piece of evidence for all this. There's this radiation filling all of space called the cosmic microwave background. This is light that was emitted when the universe was very young, about 380,000 years after the Big Bang. Back then, the universe was hot, about 3,000 degrees or so, and it was glowing. Everything was glowing with this intense light. But since then, the universe has expanded by a factor of about 1,000. And as it expanded, that light got stretched out. It got red-shifted. What started out as visible light, maybe orange or red light from a 3,000-degree glowing gas, has been stretched into microwaves. Today, that radiation has a temperature of only about 2.7 degrees above absolute zero. It's incredibly cold, incredibly faint. But it's there. It's coming at us from all directions. If you had eyes that could see microwaves, the whole sky would be glowing faintly. It's not dark at all in the microwave part of the spectrum. It's the red-shifted light from the early universe. In a sense, Olbers was right. There is light coming from all directions. It's just that it's been red-shifted so much that we can't see it with our eyes. Now, there's another piece to this, which is the finite lifetime of stars. Stars don't live forever. They're born, they burn for a while, and then they die. Our sun has been shining for about 4.5 billion years, and it'll keep shining for another 5 billion years or so. But eventually, it'll run out of fuel. It'll swell up into a red giant, blow off its outer layers, and leave behind a white dwarf that slowly cools down. In a universe that's only 13.8 billion years old, the average star hasn't even been around that long. Many stars were formed much more recently. So when we look out into space, we're not seeing an infinitely old population of stars that have been shining forever. We're seeing stars that have finite ages, and many of them haven't been shining for all that long. If the universe were infinitely old and static, not expanding, then yes, eventually every point in space would be in equilibrium. Everything would heat up to some average temperature, and the sky probably would be bright. But we don't live in that universe. We live in a young, expanding universe. So the answer to why the night sky is dark is this. The universe is only about 14 billion years old, so we can only see a finite amount of it. And the universe is expanding, which redshifts the light from distant objects so we can't see it. These two facts, the finite age and the expansion, they're both consequences of the Big Bang. The universe had a beginning, and it's been growing ever since. Isn't that remarkable? Such a simple question, why is it dark at night? And the answer tells us about the fundamental nature of the cosmos. It tells us the universe isn't eternal and unchanging. It had a beginning. It's evolving. It's expanding. All of that from just looking up at the darkness of the night sky. You know, this is one of my favorite things about physics. You start with something that seems obvious, something that everybody takes for granted, and you ask, but wait, why is it that way? And if you really pursue the question honestly, if you don't just accept the easy answer, you end up discovering something profound about how the universe works. I want to tell you a little bit more about this cosmic microwave background because it's such a beautiful confirmation of all this. This radiation was predicted before it was discovered. In the 1940s, there was this physicist named George Gamow, and he was working out what would happen in the early universe if there was a Big Bang. He realized that the early universe must have been incredibly hot and dense, and as it expanded and cooled, it should have left behind this relic radiation. But people didn't take it too seriously at first. Then in 1964, there were these two radio astronomers, Arno Penzias and Robert Wilson, working at Bell Labs. They were trying to do radio astronomy, and they kept picking up this noise in their antenna. No matter where they pointed it, no matter what time of day or night, there was this persistent hiss of radio noise at microwave frequencies. They thought maybe it was interference. They cleaned out the antenna. There were pigeons nesting in it, and they thought maybe pigeon droppings were causing the problem. They cleaned everything out, and the noise was still there. It was coming from everywhere in the sky, uniformly. Finally, they got in touch with some theoretical physicists at Princeton who had been working on predictions about the Big Bang. And it turned out this noise that Penzias and Wilson were detecting was exactly the cosmic microwave background that Gamow had predicted. It was the afterglow of the Big Bang, redshifted down into the microwave range. Penzias and Wilson won the Nobel Prize for that discovery, and it completely changed cosmology. It was the smoking gun for the Big Bang. Here was direct evidence that the universe used to be much hotter and denser, that it had expanded and cooled over billions of years. Since then, we've measured this cosmic microwave background with incredible precision. We've sent up satellites like COBE and WMAP and Planck that have mapped it out in exquisite detail. And what we find is that it's almost perfectly uniform in all directions. It has a temperature of 2.725 degrees Kelvin, and it's the same to about 1 part in 100,000 no matter where you look. But there are tiny variations, little hot spots and cold spots. And those tiny variations are incredibly important because they tell us about the structure of the universe when it was very young. Those little density fluctuations are the seeds that eventually grew into galaxies and clusters of galaxies. Now, you might wonder, if the universe is expanding, what's it expanding into? That's a natural question, but it's actually the wrong way to think about it. The universe isn't expanding into anything. Space itself is expanding. It's not like there's some empty void out there that the universe is growing into. The space between galaxies is literally getting bigger. Here's an analogy. Imagine you've got a balloon and you draw dots on it to represent galaxies. Now you inflate the balloon. The dots move apart from each other, right? But they're not moving through the rubber of the balloon. The rubber itself is stretching, and the dots are just going along for the ride. That's kind of what's happening with the universe. The galaxies aren't flying through space. Space itself is expanding, and the galaxies are being carried along. And here's something else that's fascinating. The expansion is actually speeding up. We discovered this in the late 1990s by looking at very distant supernovae. We expected that gravity should be slowing down the expansion. After all the matter in the universe is pulling on all the other matter. But what we found is that the expansion is accelerating. Something is pushing the universe apart, making it expand faster and faster. We don't really know what this something is. We call it dark energy, but that's just a label. It's one of the biggest mysteries in physics right now. About 70% of the energy in the universe is in this dark energy form, and we don't understand it. But whatever it is, it's making the universe expand faster. What does this mean for Olbers Paradox? Well, it means the situation is even more extreme than we thought. Not only is the light from distant galaxies being redshifted because of the expansion, but the expansion is accelerating, so the redshift is getting more severe over time. The most distant galaxies are receding from us at speeds close to the speed of light, and their light is being redshifted so dramatically that we can barely detect it. In fact, there are parts of the universe that we will never be able to see, even in principle. They're so far away that the space between us and them is expanding faster than light can cross it. The light from those regions will never reach us. So there's a fundamental limit to what we can observe, what we call the observable universe. Let me tie this all together. Olbers' paradox is this: if the universe is infinite and full of stars, the night sky should be bright, but it's dark. Why? Because the universe is not infinitely old. It's about 14 billion years old. Light from distant stars hasn't had enough time to reach us yet, and the universe is expanding, which stretches out the light from those distant stars, shifting it out of the visible range. These two effects, the finite age and the expansion, both come from the same source, the Big Bang. The darkness of the night sky is direct evidence that the universe had a beginning. Every time you look up at the stars and see the darkness between them, you're seeing proof that the universe is not eternal, that it started at a definite moment in the past and has been evolving ever since. Isn't it wonderful how something so simple, the darkness of the night sky, something that we take completely for granted, can teach us so much about the deepest nature of reality? That's what I love about science. You look at the world with fresh eyes, you ask questions that seem almost silly, and you discover that the answers are far more interesting than you ever imagined. And you know what else is remarkable? This cosmic microwave background that we detect, this faint glow coming from all directions, it's the oldest light in the universe. When we observe it, we're literally looking back in time to when the universe was only 380,000 years old. Before that, the universe was so hot and dense that it was opaque. Light couldn't travel freely. It was like being inside a glowing fog. But when the universe cooled down enough, atoms formed for the first time, and suddenly the fog cleared. The universe became transparent, and light could travel freely. That moment, we call it recombination, and the light that was released at that moment is what we see today as the cosmic microwave background. So when we measure the cosmic microwave background, we're taking a snapshot of the universe as it was 13.8 billion years ago, just a few 100,000 years after the Big Bang. We're looking at baby pictures of the universe, and what we see is remarkably smooth and uniform, but with these tiny little wrinkles, these fluctuations in temperature and density that would eventually grow into all the rich structure we see today, the galaxies and stars and planets. Let me give you one more way to think about why the night sky is dark. Suppose the universe were infinitely old and static. Stars have finite lifetimes, right? They burn through their fuel and die. But if the universe were infinitely old, there would have been infinite time for stars to burn, and all the hydrogen in the universe would have been converted into heavier elements ages ago. There wouldn't be any stars left to shine. Everything would be cold and dead. The fact that we have stars at all, the fact that there's still hydrogen to make new stars, tells us that the universe can't be infinitely old. It has to have had a beginning. And again, we come back to the Big Bang. You see how all these different lines of reasoning point to the same conclusion? The darkness of the night sky, the cosmic microwave background, the expansion of the universe, the fact that stars still exist, they all tell us the same story. The universe had a beginning. It's been evolving. It's not static and eternal. Now, I should mention that when Olbers and the others were thinking about this paradox back in the 1800s and early 1900s, they didn't know about the Big Bang. They didn't know the universe was expanding. They didn't know it had a finite age. So it really was a paradox for them. They couldn't solve it with the knowledge they had. It wasn't until the 20th century, with Einstein's general relativity and Hubble's discovery of the expansion of the universe and the development of Big Bang cosmology, that we finally had the tools to understand what was going on. And even then, it took a while for people to fully appreciate how the answer to Olbers' paradox was connected to the fundamental nature of the cosmos. There's a historical footnote that's kind of fun. Edgar Allan Poe, the writer, The Raven and all that, he actually wrote an essay in 1848 called Eureka, where he proposed that the reason the night sky is dark is because the universe hasn't existed long enough for all the starlight to reach us. He was thinking along the right lines. He didn't have the physics worked out, of course, but he had the basic insight that the finite age of the universe was crucial. So the next time you're out at night and you look up at the stars, think about this. Think about Olbers Paradox. Think about how the darkness between the stars is telling you something profound. It's telling you that you live in a universe that had a beginning, a universe that's expanding, a universe that's evolving. All of that from just looking at the dark sky. And there's something poetic about it, don't you think? We talk about how much we can learn from the light of the stars, all the information carried by that light. But it turns out we can learn just as much from the darkness. The absence of light is just as informative as the presence of light, if you know how to read it. This is the kind of thing that makes me excited about physics. It's not just about calculating things or memorizing formulas. It's about understanding the world, really understanding it at a deep level. It's about looking at something familiar and seeing it with new eyes, asking why, and not stopping until you found an answer that really makes sense. So remember, the universe is full of stars, billions and billions of them, but the night sky is dark, and now you know why. It's because the universe is young and expanding, and that darkness, that beautiful darkness, is one of the most eloquent testimonies we have to the reality of the Big Bang and the history of the cosmos.